Just a minute. What happened here? Okay. In yesterday's class, I have spoken about these three terms: electrocardiogram, electrocardiograph, and electrocardiography. So I told you that electrocardiogram is the graphical recording or record of the electrical activity of the heart. Electrocardiogram. The second one in the slide, that is this electrocardiograph. This is the instrument which is used to record the electrocardiogram, and the process or procedure of recording the electrocardiogram is called as electrocardiography. And we have been discussing this for the last so many times. That is about this ECG paper. Okay, so I told you about the ECG paper. Just quickly to run through ECG paper in the horizontal axis, it is time. So every small box is 0.04 seconds, and every big box is 0.2 seconds. And in the vertical axis, it is voltage. Every small box is 0.1 millivolts, and every two boxes, that is distance of 10 millimeters, is equal to 1 millivolt, right? So, okay. Uh-oh. So we looked at the two planes in which the ECG is recorded. There are two planes. Okay. So the first plane is the frontal plane. Okay, the frontal plane is going to record the ECG. The bipolar and unipolar limb leads are going to record the ECG in the frontal planes. We also have a system there of hexaxial system, which helps us to find out the electrical axis of the heart. Knowing about the orientation and electrical axis of the heart is important. Okay, so why it is important, we'll discuss down the line, because there are so many conditions or abnormalities in which the electrical axis of the heart can be deviated. So normal electrical axis of the heart is between minus 30 degrees and plus 110 degrees. So I'll discuss that maybe down the line. So this shows the leads which are there in the horizontal plane. So in the horizontal plane, you have the unipolar chest leads. So there are around 6 unipolar chest leads. I have told you about this, and it can be increased. It can go from V7, V8, V9. It can increase, right? Okay. Now this is a typical ECG, which is recorded from lead 2. So you can see that there is a P wave, okay, and you have the QRS complex, T wave, and the U wave, right? So the P wave represents the atrial depolarization. The QRS complex represents the ventricular depolarization, and it is masking the atrial repolarization. The T wave represents the ventricular repolarization, and the U wave represents the late repolarization of the papillary vessels. Okay, so moving on. There's some problem in the second batch. The pointer is, I think it's the recorded thing which is playing. Not sure how that is happening. You can also see the various segments and intervals and all that you can see. Okay. So if you remember this spread of excitation in the heart, the spread of excitation in the heart is responsible for the various waves and segments and intervals on the ECG. The heart is going to get activated in a sequential manner. So first is the atria, then you have the septal activation, and then you have the activation of the anteroseptal region of the ventricular myocardium, and then the late activation of the posterobasal portion of the left ventricle, and so on. So that is going to determine the waves in the ECG, right? So you can see here, this is how the activity is going to spread. And here the activation is from the endocardial to the epicardial surface. We have late activation of the posterobasal portion of the left ventricle, pulmonary conus, and the uppermost portion of the interventricular septum. So if you look at these two, you will understand. On the top panel, you have the excitation spreading, and in the bottom panel, you have, in the inset, you have the ECG waves developing. Please observe this very carefully. Whenever on top you have the atria being activated, P wave develops, and then when the anteroseptal region is activated from left to right, you have the small Q wave, and when the major portion of the ventricular myocardium is activated, you have the R wave, and then you have the S wave, and then when the repolarization is happening, you're having the T wave. Okay, so you need to correlate these two, the activation and so spend some time looking at this. Then I'll move on to the. Okay, now we'll try to understand what is the physiological basis of the ECG. Okay, why do you get these waveforms? What is the reason for this electrical activity to be developing in the ECG? To understand the reason for the development of waves in the ECGs, first you have to understand the concept of a dipole. So what is the meaning of di? Di means two poles are there. Okay. So in any electrical field, when you have two poles, and those two poles are having opposite charges on them, and the current is flowing equally and opposite to each other, then you have a dipole being created, as is shown in this slide which has been focused here. Okay. So you have a battery, you connect one wire to the negative terminal of the battery, and another wire to the positive terminal of the battery. So this is the one which is there to the positive terminal, and the other one here is the wire which is connected to the negative terminal. And you place these two electrodes in a solution of sodium chloride, where you have equal and opposite positive and negative charges. So sodium is positive and chloride is negative. And then when this is done, we see that current starts flowing between the two poles. So what is happening is the negative pole is going to attract the positive charges, and the positive pole is going to attract the negative charges, so that you have current flowing in two opposite directions, it is equal on both sides. The amount of negative charges flowing from one pole to the other is equal and opposite to the amount of charges flowing from the other pole. And when the two poles come closer to each other, you have more voltage being generated. And this is an example of a dipole. Now, why do you need to know about this dipole? You need to know about this dipole because in the heart you have many dipoles being created. So, how are dipoles being created in the heart? So, whenever a wave of depolarization, if you imagine my hand to be a myocardium, okay, a layer of myocardium or a myocardial cell on the cell membrane, on the outside of the cell membrane at rest, you have positive charges. And on the inside of the cell membrane at rest, you have negative charges. This is resting membrane potential. And the cell membrane in this condition, it is said to be polarized. Okay. When the cell membrane is depolarized, means a threshold stimulus is applied and it gets depolarized, reversal happens. Outside becomes negative, inside becomes positive. Okay. So when outside becomes negative and inside, connection point. Join meeting. We'll start meeting now. Hmm? Just a minute. Okay, sorry about that. So we were talking about dipole, is it not? So in the heart, you have many dipoles being created. Then how is a dipole created in the heart? So if you imagine my hand to be the cell membrane, and then you have positive charges outside and negative charges inside. Okay, this is in the resting. So in the resting condition, you have negative charges outside and positive charges. Negative charges inside and positive charges outside. Then when a threshold stimulus is applied, it is reversed. Okay. So an action potential develops, and this action potential is going to propagate. It is, it is going to propagate all along the cell membrane. Okay. So how is it going to?
Are you able to hear me?
So it is going to propagate. So when this action potential starts propagating, what happens is the negative charges, it is going to depolarize the area in front. So you have the polarized depolarized area and the one which is yet to be depolarized are behaving like two poles, just like the dipole which is shown there. So current is going to flow from the one which is already depolarized to the one area which is yet to be polarized. You have current flowing both intracellular and extracellular, from the negative to positive outside and positive to negative inside. It is flowing, and you are having a dipole being created in a solution, that is the body fluids. So now what happens is, you also have to understand that whenever current flows like this in a dipole is having two properties. A dipole is having two properties. It is having a video outlet.
Stop and start.
ఎక్కడ మ్యూట్ చేస్తున్నా.
వేరే వాళ్ళకి చూస్తున్నాం.
అది వస్తూ ఉంటుందా? Okay, in the second group is the video seen in second group. Anyone raise your hand? Was it not visible before? Right. So we'll carry on. We are having. I think this session is going to end. So a dipole is having two properties. The dipole is having a property of magnitude, means strength. The voltage can change depending on how close they are to each other and the solution and all that. And the dipole is having another property of direction. So dipole is having magnitude. The dipole is having direction. Means dipole is behaving like a vector. Okay. So the next part we have to understand, if at all you have to make any sense about what is the physiological basis of the ECG, is that in the heart, at any given point of time, many areas are getting activated. So when many areas in the heart are getting activated, there is a creation of many dipoles. It is not just one dipole like what is shown in the slide here. Like in the slide which is shown here, many dipoles are created. And what is recorded by the ECG leads is the sum of all the mean dipole is created at that point of time. Average of all those dipoles which are there acting on the surface of the heart, that is what is recorded. So I'll just repeat this concept again. To understand the physiological basis of the ECG, you have to understand a concept of a dipole. Okay, so what is shown in the diagram is a dipole. Two poles are there. That is a dipole. I'm raising two hands because there are two laptops in front of me. Don't think it is four now. Okay, so there are there are two dipoles in each two poles here, so it is a dipole, right? So in the heart, when there is a process of action potential developing, so it is depolarization. That depolarization wave spreads across the heart, and that spread of the depolarization creates two poles. One pole which is active, one pole which is yet to be activated, and current is flowing on the outer and inner surface of that active and inactive pole. I'm sorry, I don't have that slide. I'll focus it in our next meeting. Okay. So in the heart, dipoles are created. If you not understood the concept, you don't bother. In the heart, dipoles are created. Any dipole is having two properties. Dipole is having a property of magnitude, the voltage. If the two dipoles are closer to each other, more voltage is created. If they are further away from each other, less dipole is created. Dipole is having another property. Dipole is having a direction. Okay, so dipole is now behaving like a vector. Moving on, to make things slightly more complicated, and that is how God wanted it, it's not my fault. Moving on, you see that in the heart, at any given point of time, many areas are being activated. So it follows that many dipoles are there at any given point of time on the heart. So when the atria is getting depolarized, it is not that one cell, one cell, one cell, like that. Yes, somebody raised your hand in the second group. You can unmute yourself and ask the question. Whoever raised the hand in the second group, please unmute yourself and you can ask the question. Hello? Ramya? Anything? Ramya, any problem, Ramya? You can put it in the WhatsApp group. Is it audible now in the second group? Raise your hand. Is it audible now in the first group? Raise your hand. Okay. To again, quickly run through this whole thing. We were talking about the concept of a dipole. Dipole and there are two poles, two electrodes are there which are close to each other, and current is flowing from one pole to the other pole in both directions, from negative to positive side and positive to negative side, negative pole, as is seen in the slide which is focused here. You can see that the current is flowing in both directions and it is equal and opposite in direction. So you have two poles close to each other, current is flowing from one to the other, and in both directions it is flowing. In the heart also you have many such dipoles. So when one part of the heart is depolarized and there is a part in front of the heart which is yet to be depolarized in the resting membrane potential, current flows in both directions on the outer surface and inner surface from the depolarized to the polarized side. But in the undersurface, it is in the inner intracellular portion, it is going in one direction. In the extracellular portion of that cell membrane, it is going in the other direction. So when an action potential develops in the heart, and this action potential is going to move, action potential property is it is self-propagated. Okay. So when this action potential is going to move, In this process of propagation, dipoles are created in the heart. Somebody raised their hand in the first group. Any doubt? You can message me. Why are you raising your hand? Just message me. You can unmute yourself and come on to the group. First group, people raised their hand. Renuka Yadav raised her hand. What is the problem in the first group? Shall I continue? First group, please raise your hands.
Good morning, sir.
Are you able to hear me? I have unmuted you all. You can talk to me.
Yes.
I have unmuted you all. You can talk to me. I think that is better. Even though there is a lot of background noise. So much noise. Hello, can you hear me? नहीं दे रहा है क्या? कुछ तो बोलिए.
Yes, sir.
Yes,
Sir.
Shall I continue?
Sir.
Shall I continue? Second group.
Yes, sir.
Okay, please keep quiet. Why don't you go to a silent room? You are watching this video with all your family members, huh? Huh? Only you people have paid the fees. No, how can all your family members listen to this class? Huh? Have you all understood the concept of a dipole?
Yes,
I'm feeling nauseated telling that concept again and again and again.
Yes, sir. We understand.
Want me to repeat it again?
No, sir.
No, sir.
No, sir. No, sir.
No, sir.
So this is again one more look at the ECG, but you can see here that in this slide the waves are shown, and at each point of time on the ECG showing what is actually happening in the heart. Say for example, here at this point you can see that he says it is SA node is discharging. Then it is the P wave is the atrial depolarization, and then he shows the PR interval. You can just follow that. The PR interval, PR segment rather is the transmission through the AV node, and then you have the QRS complex, and then he also says that ECG cannot show the electrical activity of SA node, AV node, bundle of His bundle branches, and Purkinje fibers. Okay, and then he's showing the T wave. Then most importantly on top, he's showing you the RR interval. Are you able to see that RR interval?
Yes, sir.
Yes,
The
sir.
importance of the RR interval?
It is used
What is the
time for
importance
one
of the RR
cycle
interval?
to calculate the number of waves.
Hello?
It indicates the cardiac cycle.
Huh? What is the
Determines
Calculating the
heart
heart
rate.
RR interval?
It
Heart
helps
rate.
in determining heart rate.
Calculating the heart rate.
RR interval helps
Determining
us to
heart rate.
calculate the heart rate.
Heart rate.
See, it is like this. The PP interval will help us to calculate the atrial rate, and the RR interval will help us to calculate the ventricular rate. The atrial, the number of times the atria beats and number of times the ventricle beats is same or it is different?
Normally it is the same.
In a normal person, it will be same. But there are some abnormal conditions where you can have difference in the number of times the atria is going to beat and difference in the number of times the ventricle is going to beat. Okay. So I'll move on to the next slide. This slide is very, very, very important. This slide shows you the ECG waveform in the different leads. So one common sense question, as soon as you see that, you see, for example, in lead 1, the ECG waveform is something, whereas if you go to lead AVR, okay, lead AVR, the ECG lead is something different. Why the ECG waves are not same in all the leads? Why the reason that you get
Because they are from
different types of waveforms in different leads, same ECG, same heart, then why in the leads you are getting different recordings?
They are recorded
recording
Different
from
layers.
different directions. They are from different directions, sir.
Because each lead looks it from a different angle. Every lead looks at the heart from a different angle.
This is Yashasvi. Yeah?
Yes, sir.
Okay. Okay. So, like Yashasvi was telling, whether you are going to get. ఏంటండి అది whether you are going to get a positive lead or a negative lead, whether you are going to get a positive wave or a negative wave, an upward deflection we will call it as a positive wave, and a downward deflection we will call it as a negative wave. Okay. So when you are recording the ECG from any lead, whether you are going to get an upward deflection that is a positive wave or a downward deflection depends on the average dipole, net dipole. I told you, no, the concept of net dipole. There are many dipoles. What we record is something called as the average of all those dipoles. Okay. So whether that net dipole is having magnitude and direction. If the direction of that net dipole is towards the recording electrode or the active part of the recording electrode, you will get upward deflection. If the net dipole is moving away from the recording electrode or the active part of the recording electrode, you are going to get negative deflection. And if the net dipole is moving perpendicular at 90-degree angle from the recording electrode, you are going to get isoelectric lines. Okay, so if you look at, we'll start with lead AVR. We'll start with lead AVR. Why we are starting with lead AVR, I'll tell you, you will understand. In lead AVR, A stands for augmented, V stands for unipolar, R stands for right hand.
Right hand.
So it's a unipolar recording from limb lead right hand, right? So when you're recording from the AVR is looking at the heart from above. The mean cardiac axis or vector is moving away. The atrial depolarization, ventricular depolarization, ventricular repolarization, all these are moving away from the recording electrode. That is why all the waves are inverted. Okay. So in the other leads, say for example, you take lead 2. Lead 2, the left arm is positive, right arm is negative. So when the mean vector is moving towards the positive way, the positive side, you will get upward deflections. When it is moving away from the positive way, you are going to get downward deflections. So you can see here, so the recordings will be biphasic. In most of the waves, in most of the other leads, you will have some waves which are upward deflection, some waves which are downward deflection. Now you look at the lead V1 to V2. V1, V2, V3, V4, V5, V6. These are the unipolar chest leads. The V1 and V2 will look at maybe the atrium and right ventricle. V3 and V4 will look at most of maybe the left ventricle and a little bit of the right ventricle. V5 and V6 will be mainly looking at the left ventricle. Okay. So depending on the position of the lead, depending on the amount of muscle mass of that part of the heart which is being activated, the size of the wave, the direction of the wave is going to change. So if you look at V1, say the bottom panel, if you look at V1, you don't have very big recordings there. You have an almost insignificant P wave, a small, very small R wave, Q wave is not there, and a big S wave. You have very big S wave. You come to the same thing in V1 and V2. You come to V3 and V4, it's almost same. R wave, S wave, both are almost same. You move away, V5, V6, you see that R wave is very big. S wave is there, but it is smaller than the R wave because the position of the wave, the lead is different. The movement of the mean cardiac axis is different. The area of the electrical activity of the heart from which it is being recorded mainly is different. Okay. So this slide is very important. You can see that in the coronal section is shown. Coronal section is shown here. Okay, I'll move on from this slide. Any doubts in this slide?
No.
Doubts?
No, sir. Maulam.
Okay, when you have an ECG strip in your hand, very confusing. Where to start, how to start reading that ECG is all confusing. Okay. So how to start reading the ECG is shown here. So what is the approach for reading an ECG? So first one thing you have to do as soon as you get an ECG wave in your hand is search for P waves in all the leads. Lead 1, 2, 3, AVR, AVL, AVF, V1, V2, V3, V4, V5, V6. When you are reading it, first you look for P waves. Two participants have raised their hand here. Somebody is writing something. All the Chandana Teja. Tell me. Unmute yourself and tell me.
Nothing, sir. Nothing, sir.
You raised your hand. Please mute yourself, ma.
Okay.
Okay, so I'll just continue. You can see here the 8 steps which have been given when you want to read the ECG. Any read, first you look for the P wave. Then determine the relationship of the P wave and QRS complex. Means for every P wave, is there a QRS complex? For every P wave, do you have a QRS complex? Identify the pacemaker of the heart. Most commonly in a normal person, SI node is the pacemaker. But you can have abnormal situations where AV node is functioning as the pacemaker, or some other part in the heart has taken as the pacemaker, or there are abnormal ectopic areas of the heart which are functioning as pacemaker. So you have to determine the pacemaker of the heart. And then you have to measure the heart rate from different ways, either from the PP interval or the RR interval. So I already told you how to look at the RR interval in the slide which was shown before. Then look at the QRS complex, the shape, whether it is narrow, broad, and so on. Then examine the features of the XT segment. Most important thing which will be done. One of the most important things, look at the ST segment, whether the ST segment is flat, whether it is raised, or whether it is inverted. Usually ST segment will be flat. It is raised or inverted depending on the lead in ischemia and infarction. Myocardial ischemia and myocardial infarction, the ST segment is going to be raised and inverted. Then you have to determine the QRS axis, the electrical axis of the heart. Okay. So I told you the normal axis of the heart is -30 to +110 degrees. Usually it can be deviated. There can be left axis deviation or right axis deviation. That means there's abnormality in the position of the heart. This can happen in right ventricular hypertrophy, left ventricular hypertrophy, and blocks in the heart conducting. Okay. Then find out the rhythm, whether the RR interval duration is same. So this is done by a 20 to 30 second ECG recording from lead 2 you have to take, and by taking this 20 to 30 second ECG recording from lead 2, you look at the successive RR intervals and see whether the duration between the successive RR intervals is normal or not. Okay. So this is how we read an ECG. So first we look for the P waves, then P wave and QRS complex relationship, identify the pacemaker, identify the heart rate by looking at the PP interval or RR interval, shape of the QRS thing, ST segment. What is the importance of ST segment? ST segment will tell us whether there is any ischemia or infarction, whether there is deviation. Axis of the heart has to be determined, and the rhythm. There is another book, I think, Chike Paul, he gives the same thing in a different way. He says, look at the rate of the heart, rhythm of the heart, identify the pacemaker, then relationship between P wave and the QRS complex, QRS shape, ST segment, and then the QRS axis. Okay. So, you want me to continue or shall I stop here? We can have another session in the afternoon. If you want me to continue, you raise your hand. Okay. So, how to calculate the heart rate? The heart rate can be calculated by the simple way. You look at the number of large boxes between two RR intervals. If the number of large boxes between two RR intervals is 1, then the heart rate will be 300. If it is 2, so 300 by 2 will be 150 and so on. If you just sit and think about this, one large box One large box means it is having 5 small squares. It is equal to 0.2 seconds. So that is what is shown in the bracket there. One large box is equal to 0.2 seconds. So that is why they have come to that conclusion of 300 by 1. Okay, so this is a very simple way of finding out the heart rate. So you look at the number of large boxes between two successive RR waves, and if it is 1, 300 by 1 will be 300. If it is 2, 300 by 2, it is 150 beats per minute, and so on. Okay. Then you have something called as sinus arrhythmia. Anybody can tell me what is sinus arrhythmia? You can just unmute yourself and tell me what is sinus arrhythmia.
It's normal phenomenon.
An
in
increase
which
in heart rate during
increases
inspiration and a decrease in heart rate during expiration.
Who is this speaking?
Harshita.
Harshita. Okay. So Harshita says that sinus arrhythmia is increase in heart rate with inspiration and decrease in heart rate with expiration. So easy to remember. I and I. Heart rate increases with inspiration. Heart rate decreases with expiration. And this is very much pronounced in young adults. Say anywhere between 18 to 30 years. If you just record their pulse and you make them to breathe a little deeply, you can do it on yourself or somebody at home. You can just feel for your pulse rate. You will feel that when you inspire, there is an increase in the heart rate. And when you expire, the heart rate visibly, palpably slows down. What is the explanation for this? And this is normal. Sinus arrhythmia is not something abnormal. It is there in all of us. What is the reason for sinus arrhythmia? Anyone can just raise their hand or tell me the answer. You can unmute yourself and tell me the answer. Hello?
due to irregular beating of SNO.
Huh?
Might
Because
be
the
due to
because the intrathoracic pressure becomes negative, which creates a suction force.
Okay.
So there's greater filling of
This is
the
what?
atrium. Yes, sir.
So what? So
So
increase
there,
in intrathoracic pressure, negative suction pressure, greater filling of the atria.
so there like something called as the Bainbridge effect.
You're trying to bring in Bainbridge effect and give the explanation for sinus arrhythmia here. Huh?
I read it.
That is one of the probable explanations for sinus arrhythmia, but the more accepted one is during inspiration. During inspiration, the lungs are stretched. Agree with me?
Yes, sir.
During inspiration, the walls of the lungs are stretched, alveoli are stretched. So when the lung wall is stretched, stretch receptors are there in the walls of the lungs, which are activated. These stretch receptors will send impulses to the cardio-inhibitory center, vagal center. Okay, they inhibit the cardio-inhibitory center. Please understand this. Impulses from the stretch receptors in the lungs are sent when during inspiration. And these impulses are going to inhibit the cardio-inhibitory center. So cardio-inhibitory center is inhibited means the number of impulses coming from the vagus now to the heart decreases. Any other way this can be told? Vagal dash decreases.
Tone. Vagal tone.
Vagal tone. Vagal tone decreases. So if the vagal tone decreases, what is going to happen to the heart rate? Vagal tone is like a brake on the heart, is it not?
Increases.
Decreases.
What is the accelerator for the heart?
Heart rate.
Vagal tone is brake. What is the accelerator which will increase the heart rate?
Sympathetic discharge.
Sympathetic discharge, is it not? Sympathetic discharge is going to accelerate the heart rate, whereas parasympathetic discharge is going to decrease the heart rate, like a brake. Okay, so I'll just quickly run through this again. During inspiration, lung walls are stretched, stretched receptors, and the walls of the lungs are activated. From these stretched receptors, impulses are going to the one area in the medulla oblongata called as cardio-inhibitory area. And what do these impulses do to the cardio-inhibitory area? They inhibit the cardio-inhibitory area. So vagal tone decreases. Number of impulses going from the vagus to the heart is going to decrease, and that is going, if the vagal tone decreases, heart rate is going to increase. Okay, and that is the reason for sinus arrhythmia. You can see here very, very clearly, very nicely shown. During inspiration, you can see the distance between two R waves is more, means heart rate has decreased. Whereas during expiration, you can see the distance between two R waves here. Okay, distance between two R waves is more here during inspiration, and during expiration, this is called as sinus arrhythmia. So I want to stop here. Whether you all want to, I'm feeling very strange for me to be sitting and taking a class. Like a good boy in one place. Anyway, for the next session, I want you all to read up about something called as ectopic foci, re-entrant tachycardia. Two things. What are they? What are they? Somebody from this group, second group? Hello? Somebody from the first group? What are the two things I asked you to read?
Ectopic foci.
Ectopic foci. Circus movement, also called as re-entrant tachycardia. Somebody here in the second group? Hello? Hello? Second group, raise your hand. What are the things I asked you to read? Yashasvi. What are the things? What is it that I asked you to read, Yashasvi? Yashasvi, what is it that I asked you to read? Anybody can answer, Yamini or ectopic foci and re-entrant tachycardia or circus movement. Okay, so please read up about this. When shall we meet again? Tomorrow or afternoon? We'll meet tomorrow or in the afternoon? Tomorrow.
Afternoon, sir.
Tomorrow 11 o'clock?
Tomorrow, sir.
Tomorrow.
Okay.
Afternoon, sir.
Please get on to the sites fast. Okay?
Tomorrow.
Done?
Yes.